Okay, let's look at some things in section 5.3 along the lines of trigonometric functions and integrals involving those and the natural log. So we'll go ahead and get to the whiteboard, look at some theorems and results, and then maybe some examples to kind of help you along the way. So let me switch over to the whiteboard here. And get going on some theorems and results here. So first of all, we have some derivatives that we know. Like we know that the derivative of sine is cosine, so that we know that also then the antiderivative of cosine is sine, because once again, the derivative of the right side, if we take that, the derivative of sine is cosine, derivative of constant is 0. So we do know some of these. We know the antiderivative of sine x would be minus the cosine of x plus c, because once again, the derivative of cosine is minus the sine, and if we just want a positive sign, we're going to need this minus sign here as well. We know the derivative of tangent is secant squared. So if I have, and I'm going to use a different variable, I'll say theta. So the antiderivative of secant squared theta d theta is going to be tangent theta plus c. Once again, pretty easy checks because the derivative of the right side is the left side. The derivative of cotangent is minus cosecant squared. So if I want the antiderivative of cosecant squared theta d theta, then that's going to be minus cotangent theta plus c. And then we have some other ones as well. So we have secant the derivative of secant is secant tangent. So if I want the antiderivative of secant theta tangent theta with respect to theta, it's going to be secant theta plus c, because the derivative of secant is secant tangent. And then, of course, we have one more that we kind of know from before at least, but the antiderivative of cosecant, I'm going to go back to x's, cosecant x, cotangent x with respect to x. Well, the derivative of cosecant is minus cosecant cotangent. So since this is positive on the left side, I'm going to have the minus sign there and then plus c. Once again, taking the derivative of the right gives us the left. So we have just knowing some basic trig derivatives allows us to come up with antiderivatives, which is kind of nice. But then what we're going to do now is we're going to try and figure out what some other ones are. And we're going to be able to do that now that we've evaluated natural log and things of that nature. So here are some theorems. Once again, these are theorem is a proven fact. So we have different theorems here. Let's just look at some new ones. If I've got the antiderivative of tangent, and the book uses a u, which could be an x as well. So I'm going to use an x just to make life a little more familiar for you. But anyway, the antiderivative of tangent, well, the derivative of what is tangent? We don't really have an easy answer for that. So we're going to need to know it, live it, love it, learn it. But this is going to be the natural log of the absolute value of secant x, and then, of course, family of antiderivatives plus c. And what I really want to do is I want to prove this. So this would be an easy one to verify. All we really need to prove is to take the derivative with respect to x of the right side and make sure that we end up with tangent of x. Okay, so if you notice, this is the natural log of the absolute value of a function. So the derivative of the natural log is 1 over that. Okay, natural log of the absolute value of x is 1 over x, but in this case, it'd be 1 over secant x, and then times the derivative of what's inside. Of course, the derivative of what's inside, derivative of secant, is secant x tangent x. So if you notice, the secants will cancel out, and I'm left with tangent x. And of course, the derivative of constant is 0. So there's a very nice proof that the antiderivative of tangent x with respect to x is the natural log of the absolute value of secant x plus c. So we have a few other theorems as well. So let's just keep going with that. We also have that the antiderivative of cotangent x dx is going to end up being the natural log of the absolute value of sine of x plus c. Okay, I'm going to let you take the derivative of the right side and make sure that you end up with cotangent x, which would be 1 over tangent of x, so that would be cosine x over sine x. But I'll let you prove that. We also have the antiderivative of secant x. Secant, remember, is 1 over cosine of x, but this is going to actually be the natural log of the absolute value of secant x plus tangent of x, and then plus c. And once again, I'll let you go through and take the derivative of the right side and make sure that you end up with secant x when you do that. So we've got one more here. And so what we're really going to have is all the basic trig functions just by themselves. We're going to be able to take the antiderivative. This is also stuff that's on the front and back flap of your book, where we have these as well. So the integral of cosine x with respect to x is going to be the natural log of the absolute value of cosecant x minus cotangent x in absolute value, and then plus c. But notice the symmetry here between these two here, which is kind of nice. So we've got antiderivative of secant x is natural log of the absolute value of secant plus tangent. The antiderivative of cosecant is natural log of the absolute value, instead of secant is cosecant, instead of tangent is cotangent, and then we have a minus in between instead of a plus. So there's some nice symmetries here on that. We don't really have it on the cotangent, and that's because we're able to write it a little bit easier with the natural log of the sine of x. So we're going to want to utilize and know these for helping us take antiderivatives. So make sure that you're aware of what all of these are. So let's look at some examples along the way. And if I want to find certain antiderivatives, we could start with derivatives. Let's just look at an example here. If I've got y equals the natural log of the absolute value of tangent 4x. Now remember, that's tangent of a function then, and then plus secant 4x. Okay, if I have something like that, and I want to find dy dx or y prime, I'm going to take the derivative of both sides with respect to x. So on the right, the derivative on the right side with respect to x, so we can kind of really do this same thing to both sides. We're taking the derivative of both sides with respect to x. So the left side is just dy dx. But on the right side, the derivative here is 1 over this. So it's going to be 1 over tangent 4x plus secant 4x, but then times the derivative of what's inside, right, by the chain rule. So times the derivative of this. So when I do that, the derivative of the sum is the sum of the derivatives. So the derivative of tangent is secant squared 4x. Whoops, my screen just got huge on me. But then I've got to do chain rule again because that was tangent of a function. And so when I do that, secant squared 4x and then times 4, which I'm going to put in front of that just to make it easier on my eyes, and then plus the derivative of secant is secant tangent. So it's going to be secant 4x tangent 4x. And then once again times the derivative of what's inside here. So I'm using chain rule within the chain rule. And I've got a constant of 4 there as well. And so it's going to be times that whole thing. So really what I could do on top, you can simplify this a little bit if you want. Try and match the answer in the back of the book is always a good thing on odd exercises. This actually is odd exercise number 5 here. I'm going to go ahead and I'm going to pull out a 4 secant 4x on top and see what's left. I'm going to be left with secant 4x plus tangent 4x on top in parentheses. So these are factors. So first one times the second one. And on the bottom, I've got tangent 4x plus secant 4x, but I could actually rewrite that as secant 4x plus tangent 4x. And if you notice, what happens here is I'm able to cancel those because it's multiplication on top. So it's a basically these will cancel out to ones here. And what I'm left with is that the derivative of y with respect to x is going to simply be 4 secant 4x. So that's kind of a nice deal there as well. Anyway, that could also kind of match going the other way as well when we have if I took the antiderivative of both sides. Okay, if I took the antiderivative of that, really we said on one of our previous theorems that the antiderivative of secant is the natural log of the absolute value of secant plus tangent. And of course, we'd have a little bit of substitution we'd want to do where we have let u equal 4x and du equals 4 dx. So anyway, it kind of matches the theorem that I had put on there before going the other way on that as well. So this tends to make a lot of sense when you compare it with what I covered before we did this derivative with an antiderivative. So anyway, let's move on and do a couple of other, one or two more. Let's go into something maybe like number 31 here for an example. And what that is we're going to take the antiderivative of tangent of the natural log of x over x. We want the antiderivative of that with respect to x. Well, this looks fairly complicated. It's not a very easy thing. It's not very easy to do with algebraic manipulation. So what we need to do is try and find some tactics from chapter 4 that might make our life a little bit better here. One thing we could do is we could use substitution. Try that. So instead of tangent of a function, I would just rather have tangent of u. So we're going to let u equal natural log of x. If I do that, what's du equal? Derivative of the natural log is 1 over x. And then dx, we attach that on the right. If you notice the 1 over x dx I have right there, I'm going to be able to replace that with a du. So this is going to be equivalent to the antiderivative with respect to u. And then, of course, instead of that natural log of x right here, I'm going to be able to say tangent of u du. Now what we can do is use our theorem. The antiderivative of tangent of u du is, if you remember, it's going to be equal to the natural log of the absolute value of secant u and then plus c. And of course, what do we want to do now? We want to back substitute in what that u is. And so this is going to end up giving us natural log. This is going to be equivalent to the natural log of the absolute value of secant of the natural log of x and then plus c. So that should be the answer that's in the back of the book there. So pretty nice example. If we have a tool that works, that makes life a lot easier for us, great. We're going to use it and go from there. So let's do one that maybe doesn't work out so nice when we're trying to do things like substitution. And so there is definitely always going to be some stumbling blocks along the way. And let's see if I can find the one I'm really looking for here. If I've got the antiderivative of, let's see, 2 minus 3 sine 2x over cosine 2x with respect to x. Let's just kind of try and tackle this one. I'm just trying to double check and make sure that that's the one I actually want here. This is an odd exercise, I believe. Trying to find it here. Yeah, this is number 23. So number 23 is 2 minus 3 sine 2x in the numerator over cosine 2x with respect to x. So, you know, the reality is, what do we try and do? This is kind of an awkward thing, right? So can we make it easier? Well, we can try and make it easier. So let's do that. Let's just, I'm just gonna try and take that whole thing up there, and I'm gonna try and substitute it, and I'm gonna say let u equal what's on top, and that's 2 minus 3 sine 2x. And if I take the derivative of u with respect to x, what do I get here? I'm going to get derivative of constant is 0. That's why I went ahead and included that. And then derivative of constant times the function is the constant times the derivative of the function. Derivative of sine is cosine of that thing. But then times the derivative of what's inside is 2. So this is, and then I got to attach a dx, right? So du is actually minus 6 cosine 2x dx. And you might think, hey, cosine, you know, that looks pretty good. And does that replace this? And the answer is no, because up here, this is actually 1 over cosine 2x dx is what is actually here, because that cosine 2x is in the denominator. This does not get replaced with du over minus 6. So long story short, your wonderful substitution efforts here failed miserably. So sometimes you do things and it doesn't work. So let's try a different approach. So I'm just going to rewrite this real quick. 3 minus, excuse me, it was 2 minus 3. 2 minus 3 sine 2x over cosine 2x dx. So the other thing we could possibly do with substitution is, hey, let's go ahead and replace the bottom one. So let's let u equal cosine 2x, see if life's any better. Du, derivative of cosine, is minus the sine of 2x times the derivative of what's inside, which is 2. So I'm just going to rewrite that minus 2 out front, and then I've got the dx here. So the question is, of course, du over minus 2. We've got sine 2x dx. Well, I kind of have that, but I've got this other crud in the front here. So I've got my sine 2x dx on the last part, but really it's all of that times dx. So I think what I want to do here is I want to use algebra first, and I want to think of, if we have a minus b all over c, I could rewrite that as a over c minus b over c. So I think I want to split this fraction up and turn this into two different antiderivatives. And so I'm going to need a lot of space here. And what I've told students in the past is, do not be afraid to use a lot of paper here and show your work, because that's going to be you know, good for you, good for me to see what you're doing. So let's just use algebra here. So I'm going to use algebra. So that's kind of what I'm doing here. And I'm going to split these as a over b, which is 2 over cosine 2x dx. And then instead of the plus sign, it's a minus sign, but I can still do that. Minus 3 sine 2x over cosine 2x, and then dx. And of course, if I want, I could write that 3 out in front. Not a big deal. I could write this 2 out in front, and that's a 1 over that. So maybe I just, if it's easy to kind of erase and make it look a little nicer, I could certainly do that. And anyway, so I've got this. So the one that I was just doing was the, you know, I could let u equal sine 2x is one way to do that. So once again, if I wanted to come back here, use substitution, let u equal cosine 2x, then du equals minus 2 sine 2x. We could certainly do that using substitution there. The other thing that we could do is we could utilize the theorem that we just had. So instead of using substitution here, I'm just gonna say, hey, this is equivalent to minus 3 antiderivative. Sine over cosine is tangent, right? So this would be tangent of 2x dx. Okay, so once again, my u is like a 2x. So I do have a u here. I'm going to want to kind of clean that up a little bit. And then coming back on this other side, I've got 1 over cosine 2x. Well, 1 over cosine is actually secant. So this is going to be equivalent to 2 times the antiderivative of secant of u, which in this case is 2x dx. So this is a way that using algebra and then trig identities, when we're using kind of trig knowledge here, we can rewrite this a little bit better. And if you remember, I just gave you a couple of theorems where we actually can know what this represents, right? But what I'm going to do first, I want to make it easier here. So I want to let u equal 2x, and then du, because I want to be able to use the theorem, du equals 2 dx, which means that the dx that I have up here is going to be replaced by du over 2. Okay, so du over 2. Now, I have a 2 out here in front anyway, so it's going to be 2 over 2, because I'm pulling this 1/2 out front. That cancels to 1, which is nice. I've got the du, and instead of secant 2x, it's going to be secant of u du. Okay, so that's that one. So all of a sudden, I'm going to be able to use my theorem. We're just going to have to remember that u equals 2x. Same thing here. I'm going to let u equal 2x. And when I do that, du equals 2 dx, so du over 2. So this ends up being minus 3/2, so it doesn't quite get rid of that out there, but that's all right. Integral of tangent u du. So if you notice, I gave you 2 theorems, or multiple theorems, but anyway, these are actually in a format where we can use those theorems that are in this section on trig. So let's go ahead and do that. So this is going to equal, let me clear that off, give us some space here, go ahead and use our paper. I think I had green first. So anyway, we had the integral. So once again, we had the integral of secant u du. By the theorem, this is going to be the natural log of the absolute value of secant u plus tangent u, right? And then plus a constant, which I'm going to wait on that. Then we had minus 3/2 integral of tangent u du. And so this is going to be minus 3/2 times what? The natural log of the absolute value of secant u, right? By our theorem that I gave you earlier. And then, of course, instead of using red here, plus c, right? So we got to have a plus c on the end because it's a family of antiderivatives. And then, of course, what I want to do is everywhere there's a u, I want to back substitute now. But anyway, we used our theorems here to come up with what this is. So this is going to be equivalent to the natural log of the absolute value of secant 2x plus tangent 2x, and then minus 3/2 natural log of the absolute value of secant 2x, and then plus c. So this is a correct answer as long as we did everything correctly, which I believe we did. And since it was an odd exercise, number 23 in your book and number 1 in your hearts, we're going to look in the back of the book at the answers, and we're going to find out that it doesn't match. And that's going to be awfully frustrating. You'll be like, I hate trig, I hate calc 2, I hated pre-calc, I still hate trig. Ultimately, you hate trig, you love calc 2, you love taking derivatives and antiderivatives, but the reality is why in the world is it not the same as what the book has? because the book answer, which I'm going to put in black, so we want to go back in black in the back of the book. The book actually has an answer that says 1/2 natural log of the absolute value of cosine 2x plus natural log of 1 plus sine 2x, and then plus c. And you're saying, whoa, this is nowhere near the book answer. So should I just give up, go home? Absolutely not. So if we want to really do our due diligence, here's what we're going to do. We're going to use our trig and algebra skills and log rules and try and rewrite this stuff. So I'm going to step through that process and see if we can't match that answer that is in the back of the book there. So let's do this. First of all, I'm going to give you a little hint on what I'm going to do here. But this 3/2 here, what could I do with that? Remember, if I've got a natural log x, that's going to be equivalent to natural log of x to the a power, right? So what I can do is I can take that 3/2 up in the exponent. So I could certainly do that. So let me just, I'm not going to worry about the plus c for now, but let's rewrite this. So I'm going to have, this is equivalent to using now we have the nat, and instead of doing what I'm going to do, instead of putting the 2 x's everywhere, I'm just going to keep it in terms of u, and then we'll back substitute potentially at the very end. But anyway, what we really had here was we had the natural log of the absolute value of secant u plus tangent u. Once again, not plugging those 2 x's in just to make life easier. And then I'm raising that exponent up. So it's natural log of the absolute value of secant u. But I'm going to put that to the 3/2 power. And then, of course, we have the plus c, which as long as we got that on at the end, we're good, right? So I can kind of ignore that. So I'm actually using log rules to put that exponent there. But I'm also going to use log rules again. So I'm putting LR for log rules. So what did we have when we have, if we have the log of, natural log of a minus the natural log of b, how could we rewrite that? We could rewrite that as the natural log of, excuse me, I don't have the absolute values, a divided by b, right? So what I'm going to do is I'm going to use this log rule on this part right here. I'm going to rewrite this as the natural log of, this is going to be the top one, which is secant u plus tangent u divided by the bottom one, absolute value of secant u. So that's my a, that's my b, is right here. There's a, there's b, except that I have secant u to the 3/2 power. Yeah, so don't forget that. I had that 3/2 there. I didn't really see that. So anyway, and then of course I got the plus c at the end that nobody cares about until your final answer. All right, so the question is, how can we do this? Well, what we can do then is we can say, hey, with algebra, I'm going to use algebra here. I can rewrite this as the natural log and then just put it all in absolute values, right? So I can say secant u plus tangent u all over secant u to the 3/2. And if I'm taking the absolute value of everything, all good, and then plus c, right? So really what I have here is a fraction. This still doesn't look anything like the answer in the back of the book, but I could use the law of fractions again. So this isn't even algebra. This is like basic math. Law of fractions says that a minus b all over c is a over c minus b over c. So I can split this fraction up. And if I do that, I'm going to clear my annotations here. And hopefully you're super impressed with me being able to remember what was on the other page, and that's because I actually wrote this out. But this is going to be equivalent using algebra and laws of fractions, really, basic math. Natural log of the absolute value of secant u over secant u to the 3/2. Well, that's going to simplify a little bit, plus tangent of u divided by secant of u to the 3/2. So just splitting up the fractions. And then plus c, that once again, we only care about at the end. But let's go ahead and simplify this a little bit. So now I can use some algebraic simplification on this and say, hey, on the first part, what is this? This is secant u to the first power, right? And this is secant u to the 3/2 or 1.5 power. And if you cancel out a secant u, I could rewrite this as 1 over secant u to the 1/2 power, right? And then plus, and then over here, what do I got? Well, I'm going to rewrite this a little bit. I'm going to rewrite tangent of u is sine over cosine, sine u over cosine. So I'm also using trig rules. And then secant is 1 over cosine, right? So this part is 1 over cosine u to the 3/2, which since it's in the denominator, I can actually write it as cosine u to the 3/2 in the numerator, because secant is 1 over that. So when it's in the denominator, that's going to put that cosine up top. And then, of course, I got the plus c as well. And so when I do that, what do you know? Same type of deal. Cosine to the 1.5 divided by cosine is going to end up giving me cosine to the 1/2 on top there. So let's just kind of rewrite this a little bit here. So I'm going to go, this is equivalent to the natural log of the absolute value. Once again, secant is 1 over cosine. So I could rewrite that as cosine u to the 1/2 power. And then plus what's left over here is sine u times cosine of u to the 3/2 power. Absolute value of that, and then plus c. So we're getting a little bit closer. Oh, not 3/2. This is 1/2. That's my bad. It's so bad, I'm going to actually use an eraser here. I will erase you. I'm the Terminator. So I terminated that 3 and put the 1/2 there. If you notice, we have a common factor in two things that are getting added together. So I could actually use the distributive law, pull that out in front. So let's do that next. And doing that, I'm going to get the natural log of the absolute value. I'm going to take that cosine of u to the 1/2 power out of both terms, and I'm going to be left with a 1 in the first one, plus a sine u in the second one, and then plus c. And then all of a sudden now I can say, hey, the natural log of, remember this one, natural log of a times b is going to be the natural log of a plus the natural log of b. So the natural log of the product is the sum of the natural logs. So I'm going to do that where I have two different terms here. And I'm going to rewrite that using log rules. So once again, I'm back to log rules. This is going to be the natural log of the absolute value of cosine u to the 1/2 power. I'm going to put that 1/2 out here now. And then plus the natural log of the absolute value of the next one, which is 1 plus sine u. And then, of course, the plus c. And then, of course, using log rules again, what could I do with that 1/2? If you really wanted to, I could drop it down in front, and this ends up being equivalent to 1/2 natural log of the absolute value of cosine u. I'm going to go ahead and plug in what that u was. It was 2x, plus natural log of the absolute value of 1 plus sine 2x, plugging in back substituting what that u is. So once again, I'm using log rules again, dropping that exponent down in front, and I'm also using my back substitution, putting in what u is. And if you notice, isn't that beautiful? That's the same answer that the back of the book had. And so the good news is we now know that the book is right, because our answer before was good enough, and I know that I am. So have fun and good luck with